Hello, and welcome to Edexcel Demola. And today's video we are covering alcohols and haloalkanes. So we're going to go through the properties, reactions, and also environmental impacts of these molecules. No time to waste. Let's get into it. Okay, so we're going to kick things off by talking about the properties of alcohols. And when we're saying that, we're saying, okay, alcohols have the OH functional group, and the suffix is "ol." So you can see here, this is an alcohol because it has your OH functional group. And then also, you can see with the naming, we call them "ol." So for example, this one is in carbon 1. So you can see, if we number the carbons, is 1, 2, 3. So we'll call it propan 1-ol. If it was on the second carbon, we'll call it propan 2-ol. Cool. Propan 3-ol doesn't exist because then you just flip it to the other side. Now, in terms of alcohols, we also just need to know, okay, we have primary, secondary, and tertiary alcohols, and it's all dependent on how many R groups that your carbon's attached to. So if we look here at the carbon that's attached to the alcohol group, you can see here that we only have one R group. So this is primary. Similarly here, this one is now attached to 1, 2, so this is secondary. And this one is attached to 1, 2, 3. So then this one is a tertiary alcohol. That's going to be important later. Another thing that you need to be able to do is to just draw the bonding. So what we know is that alcohols can form hydrogen bonds, which we've covered earlier in the specification. So what you need to do when you draw this out is you need to just exaggerate this bond here. So I'll highlight it like this. You need to exaggerate this bond here. And the reason you do that is just to make your drawing easier. Yeah? So what you're going to do is you're going to draw your polarization there, also making sure to do the lone pairs, especially if it mentions it in the question. And you attach it to a water molecule. Yeah? And we've done the same things here. So when you can see that, you can see the bond going from the hydrogen to the lone pair of electrons on the oxygen, and you just label it as a hydrogen bond. That should be enough to get you your marks. And that hydrogen bonding in alcohols gives it useful properties, such as being able to dissolve in water and also being less volatile compared to alkanes. The reason why it's less volatile is because our hydrogen bonds are stronger than our induced dipole-dipole forces or our London forces. So you need more energy to overcome them, which is why they are less volatile, less likely to become gaseous. Now, we're going to get into reactions more in the next slide, but I just wanted to quickly show these ones just because I ran out of space. So, elimination reaction, what you have is you have your alcohol, and then you heat it up with an acid catalyst, and then you form an alkene. So you can see alkene and water. That's elimination, because we've eliminated that one there. Substitution as well happens. So substitution normally happens with sodium halides. So I've used sodium bromide here, but you could have used sodium iodide, sodium chloride, whatever you want. And what's just happening is this OH group gets replaced by bromine or by whatever halogen you used. Yeah, and it also forms water. And just remember acid catalyst as well. So we put the catalyst above the arrow just because the catalyst isn't actually partaking in the reaction, so it's not reacting as okay, so like we said, we have more reactions to go through. The next one is combustion, which again works very similarly to your alkanes and your alkenes. So literally, reactive oxygen, you're forming carbon dioxide or water. Now, you can either do this with structural formula or molecular formula. So you can see a structural rule is on the top, molecular is on the bottom. Either way, it doesn't really matter. And also, you can use fractions if you want to, unless the question is specifically stated otherwise. If you wanted to get rid of the fraction, literally just times everything by 2. And then that would also be fine. So say we were doing that, for example, this would become 2, this would become 9, this would become 6, and this would become 8, and then that would all still be balanced. Cool. Now here's the big one. We need to talk about oxidation of alcohols. Now, let's just quickly set the scene. Whenever you're oxidizing alcohol, we're going to use a catalyst, potassium dichromate. Yeah, acidified potassium dichromate is your catalyst. And you can either write that as K2Cl2O7 with an acid. So, for example, say we had K2Cl2O7 and then slash H2SO4. That would be acceptable. We can also write that just as the ions involved. So Cl2O7, 2 minus, and also H plus. Whatever way you say, that represents acidified potassium dichromate. And what it is an oxidizing agent, which means it's going to oxidize the alcohol. Yeah? Cool. So in turn, it gets reduced. So another important thing before we get into the actual reactions is that you need to be able to identify when a reaction has occurred. And this will come like when you're being told to prove a specific compound is present in a mixture. Yeah? And what you'll see is that the dichromate ion is orange, but when it gets reduced, because it's an oxidizing agent, so it gets reduced, it becomes green. And the idea that we get, or why we know it's becoming reduced, is just because we can use oxidation numbers. So for example, oxygen from previous should be -2. Yeah, so that's 7 times -2, which is -14. Yeah, and then we're thinking it's a 2 minus charge, so the rest of it has to be 12. There's 2 dichromates, so it's -6 left. So here, oxidation state is +6, and here you can tell it's +3. So that's why we can see that it's being reduced. Cool. Now, there are 2 different conditions that we can use when we do oxidation of alcohols. Yeah, the first one is reflux. So with reflux, what happens is you don't actually lose anything to evaporation. And because you're not losing anything to evaporation, this reaction can go on and on and on and on and on again. Whereas in distillation, you do. So in terms of apparatus, because you can be asked to draw these, this is what you want to see. So the top one is reflux, where you just have a long chamber, the condenser's on the outside. Yeah, and the other one, you can see this one where this will be your flask, and then it's going to be able to go through this middle bit here, the condenser's on the outside, and then it will go into a test tube of some sorts. So that's what we kind of want to do when you're asked to draw either reflux up here or distillation down there. What you also need to know is what is being formed in these reactions. So if we start with the top 2, these are primary alcohols. Yeah. So in a primary alcohol, we can distill or do under reflux. Yeah. And you can see all the equations there. So when we distill a primary alcohol, we form an aldehyde. Yeah. So distillation of a primary alcohol forms an aldehyde, whereas reflux of a primary alcohol forms a carboxylic acid. And all I kind of do to remember that is think, okay, reflux was the reaction going to completion, right? So because that's the case, a carboxylic acid has more oxygens compared to an aldehyde, so that will be kind of like quote unquote final state compared to an aldehyde. The 2 below, what we're saying now is, okay, we have a secondary alcohol. Now, if we have a secondary alcohol, it will only work under reflux. Yeah? So under reflux, it will form a ketone. Cool. Finally, tertiary alcohol. So you can see here, although it's not really the best when you use displayed formula, but say this is our central carbon. We've kind of got this thing going on. That's what that molecule is. So because of that, what you're saying is, okay, tertiary alcohol, they actually can't undergo oxidation. So they're not actually going to form a product. And what the thing is, again, we said dichromate needs to get reduced, right? So it doesn't actually have hydrogens to be reduced by in that compound, which is why your tertiary alcohols do not undergo oxidation reactions. So that's another important one. So if in your mixture you have a tertiary alcohol, you will not see an orange to green color change. It will just remain orange. That is a key finding, but the other ones will change. And then you'll have to use other reagents that we'll learn about, probably, I believe, in second year to identify things. But yeah. Okay, we're kind of talked down alcohols, but we are going to talk about haloalkanes now. So typically when we're talking about haloalkanes, we'll be talking about chloro, bromo, or iodo. In fact, actually, we can also talk about fluoro. So chloro, bromo, iodo, and fluoro. Yeah, those are the main ones that we want to use. And the reaction that we want to know, to be honest, properties we're not really too concerned. But reaction we want to know is hydrolysis with sodium hydroxide. Yeah, so you can see here, I'm not drawing the sodium because the sodium is a spectator ion. Yeah, if you drew the ionic equation, you'd see sodium is a spectator ion. So just using the ions that change, or the things that change, that's your equation. Haloalkane plus hydroxide goes to alcohol plus halide ion. Cool. Now, in order to identify which haloalkane we have, we can use silver nitrate. We've talked about this. Yeah. So silver nitrate, we know what colors it forms. Chlorine is a white precipitate, bromine is a green precipitate, and iodine is a yellow precipitate. So remember those because it is still important. Now, another thing that can happen is we can use this to assess the rate of hydrolysis of different haloalkanes. So in terms of bond enthalpy, or in other terms, less specific terms, bond strength, what we're saying is the carbon-fluorine bond is the strongest. Yeah, followed by the carbon-chlorine, then carbon-bromine, and then carbon-iodine. And the reason we have that is literally to do with the atomic radius. So, fluorine has a really small atomic radius because it has one shell, or 2 shells. And because of that, that's why it's going to bond more strongly to carbon. Cool. Now, the weaker we have the bond, the faster the rate of hydrolysis, because less energy is needed to break the bond, so they're easier to break. So, for example, an iodoalkane is going to it's going to hydrolyze a lot quicker compared to a chloroalkane. That's just the kind of consideration you have. Hence, it forms precipitate faster. Yeah. Another important thing is nucleophilic substitution. So, to be honest, probably one of the easier reaction mechanisms that you need to know. Nothing really too complex going on. But first of all, no, a nucleophile is an electron pair donor. So remember we said that suffix "phile" means to be attracted to. So attracted to nucleus. Think about the nucleus. Nucleus is positively charged. Hence, a nucleophile must be a negative species, which means it's going to donate electrons. So just looking at what we have here, we have one chloropropane. Yeah, you can see here, okay, our hydroxide ion is negative, so it's going to be attracted to the positively polarized carbon. And remember, we're saying that negative charges move. So we do a Cayley arrow from the hydroxide or the negative ion on hydroxide to the carbon. Yeah, if the carbon accepts that, that means that in the bond, we're going to have a heterolytic bond fission, which goes just to the chlorine. Cool? Now you just have to draw out your final product and make sure that you add this, your compound that you formed, or the ion that's formed. Very important. Last thing is just talk about environmental concerns. So really, nothing again too major. And to be honest, not something that comes up too often, but very, very important to know nonetheless, is your chlorofluorocarbons. So your chlorofluorocarbons cause ozone depletion. And you can see here some of the uses: refrigerants, aerosols, propellants is another one of them. Just pretty much stick to those and you'll get it in the exam. And the reason why these are so good is because they're stable, volatile, and non-flammable. Yeah? Really, really good properties that I just recommend just memorize. And what you do need to then be able to reproduce is this. So again, it's very similar to free radical substitution, where you can see I've got propagation, initiation, and at the end, we've got the last step there. Cool. Don't really put termination steps for this. Now, what we can see here is, okay, in that chlorofluorocarbon, so again, let's just use our imagination to see what's going on. It looks like this per se. Yeah? And you need to think which bond is going to break first. Remember, we said carbon chlorine is weaker than carbon fluorine. So the chlorine bond breaks, which is why you form a chlorine radical. Yeah? That radical reacts with the ozone layer, O3. You form another radical and you form oxygen gas. And then also what we're going to do is this radical that we form is going to react with just a singular oxygen atom, forming more oxygen gas. And an overall equation you can see is written there, O3 plus O is 2O2. So that's something that you need to know, memorize, and to be able to reproduce when it comes. Okay, you're going to earn the work today. This is a lot of questions. So you can see here we've got multiple choice to begin with, question 4 and 5 there. And then we're going to cover organic synthesis soon, but that's just kind of an introduction into what we're going to be dealing with. And then finally, last question here, you're just explaining the difference in boiling point of these different fuels. So I'm going to zoom out. Hopefully you can zoom into specific places, but those are your questions. Pause the video, give them a go, and we'll come back. Okay, so to be honest, we're going to just go to the questions to kind of explain this. I think it will work better that way, but this is an overview of the answers here. So if we look at the first one, we're saying, okay, rate of hydrolysis of iodoalkanes. So immediately we think, okay, silver iodide is going to be yellow, so we're happy to put D. Now, this one catches a lot of people out. So in terms of what's actually causing global warming, that is what we're looking at. Yeah, this D is what a lot of people go for, and yes, that's what's happening. Yes, but it's not the reason that global warming happens. So it contributes, but it's not the reason. The reason is A, that infrared radiation causes your methane molecules to vibrate more. Remember that. Now, in terms of this, so again, we're saying introduction to organic synthesis, really always focus on functional groups. So our main functional group there is alcohol. We also have alkane. So I'm just thinking, okay, alcohol, heat, and acid, catalyst. We're thinking, okay, we're going to form, and we're going to form an alkene. So we should have something like that. Yeah, that is what's going to happen. Cool. Next up, we're saying, okay, acidified potassium dichromate, so we're doing oxidation under distillation conditions. That means we're going to form, because it's distilled and this is a primary alcohol, we're actually going to form a aldehyde. Bang. And finally, if we're doing it under reflux now, that means instead of the aldehyde, we're actually going to form a carboxylic acid. So again, very similar thing, but that is now the product we form. Okay. Now, in terms of explaining the difference in boiling points or the fields in the table, we need to think what we have here. So we have alkane at the top, alkane at the bottom, alcohol in the middle. Cool. What's the difference? Well, we know hectane is 7 carbons long, hexane is 6. Pentane 1-ol is an alcohol, meaning it has hydrogen bonding. And that's really what we're going to base our answers on. So you've already seen the trend, by the way. It tells you the trend here. What you're thinking, okay, hectane just is a longer chain. Yeah, it's a longer carbon chain. So it has more points of contact, which means it will form more London forces. Cool. Pentane 1-ol is a bit different. Because it's an alcohol, it has the ability to form hydrogen bonds with each other. Now, hydrogen bonds are stronger than induced double dipole, so we're happy to say pentane 1-ol is going to have the highest melting boiling point. Then what we're thinking, okay, if hectane has more London forces, then that means that hectane will also have a bigger or larger boiling point compared to hexane. So those are considerations you need to have. Another thing is to do with branching, but I believe we've covered that in an earlier video. Okay, so finally we've got the A-star tips. So first of all, please understand the properties of alcohols and haloalkanes. Just because it's really good to add the context, especially the thing about hydrogen bonding as well. I think it relates more to alcohols compared to haloalkanes, but knowing both is very useful. Then also, this is what I'm talking, hydrogen bonding. It's a question that actually comes up really commonly, to be fair. So I think it's definitely worth being able to draw out that diagram, label the hydrogen bond, and use that as a reason to explain why alcohols have higher melting points compared to alkanes and alkenes. Also, remember and write out equations for reactions of alcohols and haloalkanes. Definitely writing out the equations is the easy bit. Yeah, knowing which equation it's going to be is harder. Right, so you're going to have to memorize this. And again, I think the next video is organic synthesis, so we're going to delve more into it in that lesson. And also reaction mechanism for nucleophilic substitution. It is the easiest one. There's 4 that you need to know. I believe this is the easiest one. So make sure you know this one really well. In terms of what not to do, previous structures is always important. So for example, there's a bit that we got from module 2 about bonding. There's a bit we got about module 3 from your silver nitrate, yeah? So make sure that you really, really are comfortable switching between topics. Ozone depletion is really important. And although I didn't emphasize it that much in this video because it's a less common question, but if it does come up, you definitely want to be able to get those marks because in the grand scheme of things, there are a lot harder questions that can come up in organic chemistry. Kali hours and charges. Reaction mechanisms catch people out so much because sometimes they'll decide to be really, really strict with the marking. So make sure your hours are really curly. The one I did in this video wasn't even as curly as it can get, but you definitely want to make sure that you can see a bit of a curve at least. So that would be fine, whereas I think that's a bit borderline. Yeah, so this one is a no-no, this one is fine. And then reagents and conditions, again, organic synthesis is the next video, so we will talk about it a lot more then. But just please remember reagents and conditions because they are easier marks to get compared to what else you're going to face in organic chemistry. So that's been it for the video today. I hope it's been really, really helpful. If it was, please like the video and subscribe to the channel. If you have any questions about anything that I've said, drop them in the comments below and I'll do my best to answer. We've also got a TikTok and an Instagram, both at @demola. Links will be in the video description below. But that's all for me for now. So thank you so much for listening. We'll catch you in the next one. Bye for now.